X, Y, Z. And then using this cuboid, we can show the stresses. So at each point, we have at each face, we can draw stresses. So sigma X, I'll draw an arrow here. So this stress, which I've shown pointing upwards, is, well, it's shear stress. The convention is uh, the first subscript is the direction, that is the plane along which it acts. The plane is X. Okay, the plane is defined by the normal to the plane. So the normal to this plane is the X plane. And then the second subscript is the direction. So the direction here is Y. And then for this one, we can draw another arrow here, and that would be tau. Again, face is X, direction is Z. And then we can keep doing that for other faces. Sigma Y. Tau, face is Y, direction is X. Tau, face is again Y, direction is Z. And then just one more left. Take it this face, which is right here. Sigma Z upwards. So that would be tau, face is Z, direction is Y. Draw it here. The face is again Z. And the direction is X. Yes, so the pink and the red is the face I have for the first one. The blue is, let's see if I can change this to blue. So this is going to be the face, which is right, the first face you see when you look at the picture. And then it's to the three, this is the last face. Okay, now this is just showing the stresses on three faces, but really there are six faces to a cuboid. So, the same stresses can be drawn on the other side with exactly the opposite directions. That way the stress element is in equilibrium. It's not moving. So what I've shown here is the stresses. Let me write them here. So sigma Z, tau Zy, tau Zx. Then I wrote sigma Y, tau Yx, tau Yz. And then finally I have tau sigma X, tau Xy, tau Xz. So you can see that there are 9 stresses. Okay. And the way we can analyze these stresses is we just lump them together the way we've lumped them. So we can do sigma X, sigma Y, tau Xy equals tau Yx. So this would be 3 stresses in XY plane. You could club the sigma Y, sigma Z, tau Yz equals tau Cy. That would be 3 stresses in YZ plane. Third one is sigma Z, sigma X, tau Zx is tau Xz. This would be the 3 stresses in XZ plane. Just makes your life easy by considering them as three plane stress elements in three different planes. So we've drawn the one in the XY plane, but you could do the same thing for the YZ and the XZ plane. Okay. Now, how does this connect with the Mohr circle? Because there are three stresses, you can actually draw three Mohr circles. So that the way to do this is is as follows. So we draw three Mohr's circles for 1, 2, 3. These being, oh, sorry, 1, 1, 2, 3. So let's say that after drawing the three, when you talk about Mohr circle, you're talking about the principal stresses, sigma C. So for a 2D Mohr circle, we had two stresses, sigma A, sigma B, because there are three principal stresses. Because there are three-dimensional plane. You will have essentially three principal stresses: sigma A, sigma B, sigma C. So then what you'll do is you will compute those stresses. Then you would rearrange them such that the first stress is greater than second one, greater than third one. So let's say that you get I don't know, 5, 10, and 1. Okay, I just made up some number. So then you just rearrange them so that this is 10, this is 5, this is 1, or you'll rename them as sigma 1, sigma 2, sigma 3 based on the value of the stress. And once you have that, so rearrange in descending order. Okay, then you can draw three more circles. You'll have one big Mohr circle. And then two smaller ones. Okay. Now these values are going to be sigma 1, sigma 2, and sigma 3. Okay, again, remember that we arrange in some order. So sigma 1 is always greater than sigma 2 is greater than sigma 3. Then the other thing is see the centers here. So this is the center of the biggest circle. This is the center of the next circle, and then this is the center of the last one. Okay, now this height for the radius is actually the maximum shear stress for the largest circle. It's because abbreviated as tau 1, 3. This one is between 2 and 3. So tau 2, 3, and this one is tau, tau 1, 3, tau 1, 2. This is tau 2, 3. Okay, so here sigma, or sorry, tau 1, 2, 1/2 is nothing but, you can see that just from the figure, it is going to be the average, or sorry, the difference in the x coordinate of sigma 1, sigma 3. So the x coordinate of the diameters of the circle divided by 2. And then we have tau. So that should be tau 1, 3, my bad. And tau 1, 2 would be r equals sigma 1 minus sigma 2 divided by 2. And then finally, tau 2, 3 will be sigma 2 minus sigma 3 divided by 2. So the main thing which we'll come back to later on is that when we're talking about the stresses and we want to look at failure, we typically look at the maximum possible stress. So in this case, the maximum possible stress is, okay, let me just get this. Okay. So the maximum stress, principal stress is sigma 1. So that would be possibly be used in design. Another thing we notice is that uh, the maximum shear stress is actually tau 1, 3. Okay, tau 1, 3 comes from sigma 1 and sigma 3. Okay, sigma 2 doesn't really matter here because it's not the critical stress. So it's only 1 and 3 which gives you sigma 1, sigma 3, which gives you the maximum shear stress. So if you are looking at failure, which uh, there are certain criteria about failure which depend on the shear stress, then you would work with tau 1, 3 because that's the biggest stress, biggest shear stress. And then for normal stress, you perhaps will deal with sigma 1. So there is an entire list of failure theories which use different stresses in order to design the material, and they actually come from the Mohr circle. While looking at this Mohr circle and figuring out the worst case stress. So this is going to come back again to us a little bit later. But I want you to know that this is what you would typically use when you are trying to design something of a handbook containing tables and charts of stresses, and if you're told to deal with a particular theory, which is again something we'll talk about in detail in a little bit later in this course.